This microlecture is on drying and densification. When you have a chance, please visit the attached link on the largest biomass energy plant in the world. It is located in Poland and it is rated at 205 megawatts. It will utilize over 1 million tons of biomass every year, 80% of which should come from purpose-grown tree farms. Please take a moment to review this week's learning objectives. Drying is important. Biomass is almost always wet, and often at least some of this water has to be removed before it can be used or processed. Drying is a very expensive and often overlooked step in using biomass. These are some images of direct heating dryers. The cheapest way of drying is called direct heating. These dryers blow hot combustion air directly on the feed that needs to be dried. While this is cheaper and easier, it is also harsher and much more prone to damaging the biomass. For this reason, direct heating dryers are not all that common. This is an image of an indirect heating dryer. These dryers contact the feed that needs to be dried with some kind of heat exchanger. Indirect heating is more expensive, but much more controllable than direct heating. As a result, it is also more common these days since it is safer and often more manageable. This should make it fairly clear that drying biomass is expensive. A BTU measures how much energy is needed to heat 1 pound of water by 1 degree. A gallon of water weighs 8 pounds, so it should take about 350 BTUs to make it boil if it is sitting in a pot and being heated with perfect efficiency. Sadly, in the real world of thermodynamics, perfect is not an achievable thing. Biomass drying requires a massive source of energy because removing the water from biomass is harder than getting it to boil out of a pot, and wood dryers are not all that efficient because it's hard to heat awkward solids like biomass. As a result, we end up requiring a lot of energy to dry biomass. In many ways, pellets are looking like the future of small-scale biomass combustion. They are much, much easier to handle than firewood, and like was previously mentioned, they are an engineered fuel, so they can be used in a precisely engineered manner, which increases efficiency and uptime. Pellet plants are operating all over the nation, and in many states they have taken over plants that were previously used to produce particle board and fiberboard. New designs for better utilization of pellets are happening all the time, and this area of bioenergy promises to be an interesting area of development for years to come. Pellets are an excellent way to take loose biomass and make it uniform and high density. You can make pellets from any solid you can get to flow. It's amazing to look at pellets and think about how different all those sources are, but yet the pellets look similar and would probably work in similar systems. This would be like being able to put gasoline or diesel into the same engine and have it work just fine. So being able to make pellets from anything is a big deal. The pellet mill is almost the opposite idea of the grinder or chipper. The goal of the pellet mill is to combine small materials into larger pieces, rather than breaking large materials into smaller pieces. It uses a die and compression to make this happen. As this happens, quite a bit of heat is generated from all the friction. This heat tends to melt some of the lignin on the outside of the pellet and gives it a harder surface. When you hold a wood pellet and notice that it's hard on the outside and a little shiny, that's because of this lignin melting and reforming process. Pelletizing doesn't work well with all forms of carbon, but it works very well with biomass. Pellets do not change the chemical composition of the biomass. They just change the form the biomass is packaged in, and by doing so noticeably increase the energy per unit volume. So, you get way more biomass energy per gallon than you would if it wasn't pelletized. This does different things for different sources of biomass. Corn stover, for example, goes from being a poor fuel as a loose biomass to being as compelling as something like sawdust after it's turned into a pellet. It is important that we are clear about pellets increasing energy per unit volume compared to energy per unit mass. Once more, pellets increase energy per unit volume. If you want to increase energy per unit mass, the most desirable conversion is thermal to make charcoal, not mechanical, to make pellets. Making charcoal changes the chemical composition of the biomass and increases its energy per unit mass. So something that is 10 BTUs per pound can become 13 BTUs per pound. This table tries to make this comparison between wood pellets, and charcoal. Pellets have become a major global industry. It is hard to imagine using 54 million tons of wood pellets, as shown in the graph here, by 2025. Pellets sell for around $250 to $300 a ton, so that's a lot of money in pellets. Only a few parts of the world grow enough wood to support that level of demand, and North America is one of them. So this is an area worth paying attention to. Pellets sound a little silly in our current world of natural gas until you consider availability and market conditions. Pellets are easy to store and easy to produce when needed, so they don't require expensive liquefied natural gas facilities, and they aren't subject to the same market fluctuations because they are more distributed and less centralized. This is very clear when looking at natural gas and pellet price fluctuations. There are some very good strategic reasons to consider pellet heating. On the whole, because they are produced by a renewable resource, pellets have a lot going for them. They are also not nearly as carbon intensive to produce as liquid fuels, so they are much more sustainable than biofuels as well. A car that efficiently ran on pellets would be quite a thing. The article in the attached link is about a tar lake in Trinidad. As the world fights over oil, it is always interesting to think about how there are still lakes of oil all over the world that aren't considered for production. They aren't considered because the oil is low quality compared to what we use today, but that is becoming a silly idea as we watch the tar sands of Canada and shale oil production continue to become more commonplace. I don't know how long it will be before we consider trying to produce oil from these tar lakes and tar reservoirs, but it certainly casts light on the complexity of what technically recoverable reserves means and what the future of hydrocarbon on Earth looks like.